Hi, we're a team of Ventures, and this is our design review for the SWE BWSI Build a CubeSat Challenge. In order to ensure that our CubeSat has all of the necessary capabilities in order to operate properly during its mission, we've created a brief list of SMART requirements. These requirements include guidelines for the CubeSat to fit within its 10 by 10 by 10 centimeter UI size requirements, being able to turn on and off, having the IMU be able to sense different values when shook, all the way to the CubeSat needing to identify plastics in the pictures and being able to send the data found in the pictures back to the ground station. All of these requirements shall be implemented through extensive testing, inspection, and exhibition to ensure that they're being executed properly.
Okay, so this is the Conops diagram. So in the beginning on the left, we start the CubeSat on power off, and then it switches on, and then we start the pre-launch testing. And if our CubeSat passes the pre-launch testing, we can get ready to launch. And then after we launch, the CubeSat will be deployed and set into orbit. And then once it's in orbit, it will conduct a self-test to make sure all the parts are working well, everything's in place. And if it passes that self-test, it'll start up the camera. And once it starts up the camera, it'll get ready to take low resolution pictures, given the constraints that we've coded to make sure that plastic is being taken in the picture. And then once the low resolution picture is taken, it'll be sent back to the ground station, and then we'll manually look through the pictures and find a picture that we are interested in looking deeper into, and then we'll send those coordinations back up to the CubeSat, and then the CubeSat will go to those coordinations and they will take high resolution pictures. So there are many places where a CubeSat could fail to do certain parts of this diagram. So if we start off in the beginning, it could fail to power on. And then if that happens, we would restart the system and try reconnecting. And then for the pre-launch, we'd have to fix bugs. And then for the launch, we'd have to do a complete system restart. Same with orbit and things like that happen. So if that happens, any type of error, we will always go to doing a system restart. And if the system restart doesn't work, like the CubeSat keeps failing over and over again, then the CubeSat will go into failure. So here is the visual of the Conops in space. So these are the steps of how the CubeSat will be launched. So first, the rocket with the CubeSat inside will be launched, and the CubeSat will move into orbit. And once it's in orbit, the CubeSat will start orbiting Earth, and it'll start to take a specific amount of pictures, and then it'll recharge and stay idle during the dark side of the Earth. And then it'll have constraints of when to take a picture, so there's a better chance of having a picture that has plastic in it. And at first, the CubeSat will take low resolution pictures and it will record the location, so the coordinates, the longitude, the latitude. And then the CubeSat will come near proximity of the ground station for like a period of 1 to 3 minutes where the connection is very strong. And then the CubeSat will send in the pictures that it took during its orbit. And then we will manually find pictures that contain plastic in the ocean that we think meets our requirements. We'll push those coordinates back up to the CubeSat, and then we'll send the CubeSat to that area to take more pictures in higher resolution.
To begin to explain how the CubeSat shall operate in space, here in our system level block diagram, we must consider how to receive its power in the first place. While in orbit, the CubeSat's solar panel shall be able to capture sunlight and be able to generate electricity through the photons it collects. Then, some of the energy is stored in the power bank in order to ensure the CubeSat has enough energy to operate when in an eclipse, and the rest goes into the Raspberry Pi. Yet, in terms of our CubeSat, we will be mostly focusing on extracting the power from the power bank to use rather than our solar panel due to its low wattage. Next, once the Raspberry Pi receives power, it'll be able to take the necessary pictures by sending power to the camera through its flex cable whenever it is prompted to do so based on the values it receives from the IMU.
Architecture, there are going to be two orbits. For the first orbit, it's going to start with a directional state, where it uses attitude control to make sure it's in the right position before taking pictures, and so it's actually facing Earth and the oceans. Once it's facing the right way, it's going to begin to take low-resolution photos every 1,000 seconds or so. And once that data is gathered, it's going to do absolute basic analyzing of the photo to see if there's plastic in it or not. If there is no plastic, it's just going to delete the photo to save room in the Python. But if there is plastic, it'll save the photo along with the coordinates of where it was and then continue the process. If the CubeSat goes into a dark zone, it'll start rest mode, where it's idle and it's saving power and it doesn't take any photos. It's going to continue taking pictures until it's completed its orbit and it's above the ground station, where it will send these saved photos and the coordinates in a batch to the ground station when it's nearby. It'll check to make sure that the station actually receives these photos too. For the second orbit, it's going to repeat the directional stage, but it's going to also use the coordinates saved from orbit 1 in order to make sure it's taking pictures of where the plastics actually were. Once it's in the right position, it's going to take high-resolution photos this time every 75 seconds or so. As mentioned before, it'll go into the rest mode once it's in the dark zone, and once it's completed the second and final orbit and it's above the ground station, it'll send all these saved photos with actual plastics in them to the ground station so that it can analyze these photos further.
As for a mechanical layout for a CubeSat, it shall consist of two levels, the top level consisting of our power bank, while the bottom level consists of our Raspberry Pi and IMU. On the top, we have our solar panel, which will be able to receive energy from the sun, while our camera faces the other side, being able to take pictures of the Earth's oceans. The solar panel shall be able to connect to the power bank through a hole on the top acrylic panel, while the power bank will be able to connect to the Raspberry Pi with a USB cable through another hole in the paneling.
The link budget is what we calculate to see if the link between the transmitter, in this case our ground computer, and the receiver, our CubeSat, can be closed, and how much data at what rate can be sent back and forth. We calculated this from gathering the following parameters like frequency, the distance of orbit, bandwidth, and our transmitter and receiver power relative to our devices and the Bluetooth connection that we will be using. After calculation and testing, we estimated the uplink SNR to be 12 decibels and the downlink SNR to be 12.3 decibels. The SNR is the signal to noise ratio and indicates how much the signal will be picked up eventually by the receiver. Since Bluetooth uses a pretty large bandwidth of 2 MHz and the distance of our orbit, the constant being 3 meters, the error rate is fairly less and the Pi still has a sustainable RSSI to keep up with the data flow and signal capture. The estimated data rate is 2 Mbps for low energy Bluetooth. However, the estimated bit error rate will definitely fluctuate as the SNR and Pi's RSSI varies upon factors like distance of orbit affecting the transmit and receiver powers, the size of the data, and more importantly, other objects or Bluetooth devices which affect noise. Our link margin from the necessary data rate should still allow us to close a link inclusive of these factors.
In terms of our CubeSat's power budget, we'll have 4 devices receiving power, such as the Raspberry Pi, its camera, and the IMU, and we'll have 2 devices proffering power, both of which being the power bank and the solar panel. As you can see from the calculations on the slide, when our CubeSat is in orbit, it'll have around 36 watt-hours worth of power in the power bank, while the solar panel will be able to provide 0.12 watt-hours worth of power every hour. When it comes to the power usage of the Pi, It only takes about 2.514 watts per second when it's idle, and in order to complete the picture taking needed for its first orbit, it'll need around 1,619.918 watts of power to take the amount of pictures needed, which would be around 532 pictures, and in order to complete the necessary picture taking for its second orbit, it needs to use around 320.164 watts of power for 94 pictures in higher resolution. Keep in mind that, as the Raspberry Pi only consumes around 3 watts per second for both pictures of resolution, for around 6 seconds, the wattage shall be subtracted from the 129,600 watts per second wattage. As for the budget, in order to ensure everything is in order for our CubeSat, we have all of our electronics, from our Raspberry Pi to our IMU, all the way to our sphere hardware, from our acrylic panels, side brackets, screws, nuts, and nylon standoffs included in our bill of materials. By the end of these measurements, we found that our total cost sums up to $304.10, while our total mass sums up to 493.918 grams.
The Raspberry Pi storage capacity is 16 gigabytes, and out of that, we're using 14 to store images. In the first orbit, the CubeSat will take low-resolution pictures. Based on the file size of each picture, our device can store up to 538 images. Then, they will be grouped and sent to the ground station. When we use the JPEG compression algorithm, we can reduce the file size by 10%. At that station, the images will be processed to identify any possibly polluted areas. If identified, we will send the CubeSat towards that location again to take higher resolution pictures. Based on their file size, the CubeSat can store about 94 images. The images taken will be sent to the ground station again and be further processed to correctly identify pollution.
The structural aspect of the CubeSat is important to the infrastructure since the quality of the structure is what determines how successful a CubeSat is in space. Structural data is important to consider when planning for temperatures, takeoff, and landing. Power is also crucial since every part of hardware in the CubeSat needs power in order to function. The solar panel will allow a constant source of energy while the power bank stores it to use when needed. Communication is key to ensure that the parts of the CubeSat can interact with each other and properly send each other data, from the signals from ground station, the sensors and camera detecting trash, and the Pi sending images to the ground station. ADCS, another part of the CubeSat, is responsible for receiving cues from the many sensors of the CubeSat and ground station and using them to adjust its position as needed in order to ensure that it can find the trash and take a picture of it. Command and data handling is an aspect that monitors and organizes the flow of data occurring between the Pi, IMU, camera, and ground station. Additionally, in order to test the function of the CubeSat, we plan to place garbage in an inflatable pool and wave the CubeSat over the pool at different heights to test detection, image capturing and processing, communication between Pi and IMU, and receiving and sending of information between Pi and ground station. To test the temperature maintainability, we can place the CubeSat in the fridge and ensure that the CubeSat can withstand the freezing atmosphere of space.